Hello, thanks for clicking on this Prenarculus production. Today we're going to be talking about rational functions. This is an introduction to being able to graph rational functions. We're not going to graph them here on this video, but we're going to start talking about all of the things that you need to be able to do to graph a rational function. All right, so let's get started with some of the things that we need to look at. Okay, so first, let's start with a rational function. A rational function is just the division of two polynomial functions. So far we know how to graph polynomial functions. For example, if I gave you f of x is equal to x cubed plus 2x minus 1, we sketched that in the last section. If I told you g of x was equal to x squared minus 4, we could graph that, or you could graph it using the stuff we learned in the last section with cross and bounce. But today we want to talk about rational functions, which would be the division of these two functions. So for example, what would this function look like? That's what we want to learn here. Okay, what if we take two polynomial functions and divide them? What would the graph of that thing look like? All right, so that's the idea behind this section. Okay, so first, in this video, we're going to learn a bunch of the things that you need to be able to do to graph a rational function. We're not actually going to graph it, but we're going to learn the things that you need to be able to do to get the graph of it. Okay? All right, so a lot of these things you've seen before. They're a little more formalized than they were earlier in previous sections, but you're going to see some common themes here as we go along. Okay? So let's talk about finding the domain of a rational function. So you're going to find the restrictions in the domain by setting the denominator equal to 0 and solving it, right? We've done that so far since chapter 1. Okay, so let's do that with this function here, and then we'll talk about discontinuities. So we're going to take x squared minus 6x plus 8, set it equal to 0 to find our domain. Okay, now, what am I going to do with x squared minus 6x plus 8? Well, I'm going to do what I do most of the time in this class, and I'm going to factor it. So I factored it, x minus 4 times x minus 2. And then I can split these two and solve them both. So x minus 4 would equal 0, x minus 2 would equal 0, x equals 2, and x equals 4. So x can't be 4, x can't be 2. So now to write my domain, that would be pretty easy, right? If you want to make a number line, just to make sure you know how to write it in interval notation. Can't be 2, can't be 4, but it could be anything in between. It could be that, it could be that, it could be that. So my domain is going to be negative infinity to 2 in the union with 2 to 4 in the union with 4 to infinity. So that's my domain. That's how I find domain. I've been doing it since chapter 1. It's the same thing you've been doing so far. Now, what we're going to do is we're going to take these two values, this x equals 4 and x equals 2, and we're going to classify them further. So, by definition, we call these two values discontinuities of the function. Okay? These are discontinuities. We know x can't be 4, we know x can't be 2. But what we want to be able to do is we want to be able to classify these two, because there's two types of discontinuities. We call them removable and non-removable. Okay, each one is a certain definition, which we're going to talk about coming up in a moment. All right, so we're talking about two different types of discontinuities: removable discontinuities and non-removable discontinuities. So we're going to take now our domain where x can't be 4 and x can't be 2 and take it one step further. All right, so let's go to the let's keep going, and we'll talk about the first type of discontinuity. So the first type of discontinuity that we want to classify is a removable discontinuity. A removable discontinuity is a hole on the graph. Okay? So by hole, we just mean it's an open circle somewhere on the graph. So my physical graph, it might look like this, but then all of a sudden, you actually have a hole in the graph, and then the graph would continue on, whatever that may be. Okay? This hole is called a removable discontinuity. So we're going to be able to figure out what that looks like algebraically here, because we have to be able to recognize it when we go to graph our function. All right, so let's take a look at this one. Removable discontinuities are discontinuities that can be removed by simplifying the function. All right, so let's go find the domain first. Okay, so we know how to do that. So to find the domain, I'm going to take the denominator, set it equal to 0. It can't be that number, so x can't be -1. I know that for certain. So my domain is -infinity to -1 in the union with -1 to infinity. However, this is my domain. That is the correct answer for that. Now, x equals -1 is a discontinuity. So I want to go one step further now. And you can do that by going back to the original function after you find the domain and try to factor it and cancel out the discontinuity that you just had a moment ago in the denominator. So if I take x squared plus 5x plus 4, it's going to factor. It's going to factor as x plus 4 times x plus 1. And now, if I'm dividing that by x plus 1, all of a sudden, these x plus 1s, they cancel out. I just removed the problem that I had with the domain a moment ago, which means x equals -1 is a removable discontinuity. Okay, it's called removable. Now, what it means is that there's going to be a hole in the graph at the point where x equals -1. So there's a hole in the graph when x equals -1. To find the y value for that hole, because remember, when you go graph on the coordinate plane, you need to have an x and a y coordinate, right? So to find that y value, we're going to take -1 and we're going to plug it into the function that we just crossed out, okay, that we just simplified. So now, if I take g of x, which I'm now calling x plus 4, and I plug in -1, I get -1 plus 4, which is 3. So there is a removable discontinuity, okay, on this function. It's a hole at the point where x is -1 and the y value for it is 3. So when I go and graph my function g of x, okay, I'm literally going to put an open circle on the graph at the point -1, 3. That's what that means. That's what we're doing here. Okay, we're finding a removable discontinuity. That's what we found. All right, that's an example of a removable discontinuity. Okay, so let's talk about a non-removable discontinuity. Non-removable discontinuities are vertical asymptotes. So the graph is literally going to have a vertical asymptote on the graph so that the graph itself won't be able to cross it. Okay? A vertical asymptote is a discontinuity that cannot be removed by simplifying the function. All right? So let's find the domain for h of x. So step 1, let's find that domain. So to find that domain, the denominator, x cubed minus 6x squared minus 4x plus 24 can't be 0. So now I got to be able to do something with this, so I'm going to factor it. Okay, it's got 4 terms. I'm going to factor it by grouping. So if I can group these, there we go. So my first GCF is x squared. It leaves me with an x minus 6. My next GCF is -4. Leaves me with an x minus 6. Okay, can't be 0. Take out the x minus 6. And I get an x squared minus 4 left over. Now the x squared minus 4 will factor again. So it'll give me x minus 6 times x minus 2 times x plus 2. Okay, x squared minus 4 factors is the difference of two squares. And now I have 3 discontinuities. Okay, x can't be 6, x can't be 2, and x can't be -2. So my domain for this is quite lengthy. I'm going to come up here. So my domain is going to be from -infinity to -2, -2 over to 2, 2 over to 6, and then 6 to infinity. Okay, you want to see that on a number line, just so that you have an idea. You understand where all these intervals are coming from. I got -2, 2, and 6. It can't be that. It can't be that. It can't be that. But there's 1, 2, 3, 4 intervals there that it could be. That's all of them. All right. Okay, now, these are my 3 discontinuities. All right, so I got discontinuities at those 3 values. Now, I want to classify them. I want to know if they're removable or non-removable. Okay, so I'm going to go back to my original function here. And my original function, I'm now going to try to factor the numerator. The denominator is already factored, so I'm just going to write that down. I did that to find the domain, right? You have to find the domain first before you can classify the discontinuities. Okay, I'm going to factor the top. The top factors as x minus 6 times x plus 1, right? Now, here's what happens. The x minus 6's, they go away. And I'm left with x plus 1 over x minus 2 times x plus 2. Now I'm going to analyze what my denominator looks like. All right, so what I did was I removed the x minus 6's. Okay, so that 6 as a discontinuity is, I now know it's removable. I took it out. But the x minus 2 and the x plus 2 are still there. I can't remove them. There's nothing to cross it out with up in the numerator. So these are non-removable. These are non-removable discontinuities. Okay, so now here's what I know. I have a non-removable discontinuity at x equals 2. That means that line will be a vertical asymptote on the graph. I have a non-removable discontinuity at x equals 2. That will also be a vertical asymptote. Okay, and then I have a removable discontinuity at x equals 6. So that's a hole. And I have to find the y value that goes with it from the previous slide. All right, so to find the y value, I'm going to take x equals 6, and I'm going to plug it into my function that I just canceled with. So I have h of 6 would be 6 plus 1 over 6 minus 2 times 6 plus 2. So that's 7 over 4 times 8, 7 over 32. So there's a removable discontinuity, a hole at the point 6, 7 over 32. So when I go to graph this function, okay, when I go to graph it, there's going to be a vertical asymptote on x equals -2. There's going to be a vertical asymptote on x equals 2. And there's going to be a hole at the point 6, 7 over 32. There's literally going to be an open circle on the graph. I don't know what the rest of the graph looks like, but I know all 3 of those things already. Okay, those are my 2 types of discontinuities. We're going to practice that later on too when we kind of put the whole thing together. All right, those are your first 2 steps in being able to graph a rational function. Okay, now we talked about vertical asymptotes just a moment ago. Now it's time to talk about horizontal and slant asymptotes, because these graphs can also have horizontal or slant asymptotes. Slant asymptotes meaning asymptotes that look like the equation of a line y equals mx plus b. Okay, so literally they can actually be slanted. All right. So to find a horizontal or a slant asymptote, you need to compare the degree of the polynomial, the largest variable exponent. We talked about this in the last section when we looked at end behavior in both the numerator and the denominator. There are 3 things that can happen here. If the degree of the polynomial in the numerator comes out to be equal to the degree of the polynomial in the denominator, you divide the leading coefficients to find the horizontal asymptote. So on this polynomial, we have a degree 2 in the numerator. We have degree 2 in the denominator. The degrees are the same. So I'm going to find the 2, okay, leading coefficients. So that's the 4 that's in front of the x squared there. The -7 is in front of the x squared there. And I know that there will be a horizontal asymptote at the line y equals 7 or 4 over negative 7, or negative 4/7. Okay. Again, remember, y equals are lines that are horizontal, right? Lines that have equation y equals a number are lines that are horizontal. Okay. All right. So my asymptote here would be at y equals negative 4 over 7 for a horizontal asymptote. Okay. That's the first case that could happen. The next thing that could happen is the degree in the numerator could be smaller than the degree in the denominator. For example, in this polynomial, I have degree 1 up on the top. On the bottom, it's degree 2. So if the degree on the bottom in the denominator is larger than the one on the top, then it's automatically a horizontal asymptote. Okay, or automatically a horizontal asymptote at y equals 0. So literally, there'll be a horizontal asymptote running across the x-axis. All right, there's no work to do for this. You just look at the degrees. If the degree on the bottom is bigger than it is on the top, it's done. And there's a horizontal asymptote there at y equals 0. Okay, that's case 2. That's the second thing that can happen between horizontal and slant asymptotes. The third one is everyone's favorite, case 3. If the degree in the numerator is 1 larger than the degree in the denominator, you need to long divide to find the slant or the slant asymptote in a form y equals mx plus b, the equation of a line. So if you look at this one here, we have degree 2 up top, degree 1 on the bottom. The degree on the bottom is 1 smaller than it is on the top, so I need to long divide this. Now, this one has a linear denominator, so I could actually synthetically divide if you wanted to. I could put 3 in the box, 5, negative 7, and 2 are my coefficients. Don't forget, if you have anything missing, you got to fill it in with a 0. Bring the 5 down. 3 times 5 is 15. That's an 8. 8 times 3 is 24. 26 is my remainder. Now, when you're looking at the slant asymptote, you actually ignore the remainder. Okay, you ignore the remainder completely because the form of the asymptote has to be the equation of a line, y equals mx plus b. And you can see we started here, this polynomial with degree 2. So now this will go 1 down. So it'll be degree 1 here plus 8. So my slant asymptote is the equation y equals 5x plus 8. And that's the equation of a line, right? With slope of 5 over 1 and y-intercept 8. So you literally have to graph this line, okay, y equals 5x plus 8, to draw the slant asymptote. All right? Those are your 3 cases. Those are the 3 things that can happen. Anything else, we would say there's no horizontal or slant asymptote. All right? Anything else that happens, we'd say there's neither one. If anything other than case 1, 2, or 3 shows up. Okay? All right. Again, that's something we're going to practice momentarily here when we look at a couple of examples. We're going to try to put it all together. But that's something that you have to know. You got to know all 3 cases. Okay. Finally, intercepts, right? So your x-intercepts. To find an x-intercept, you set y equal to 0. Now, when you set a rational function equal to 0, the zeros show up when the numerator is equal to 0. So my x-intercepts are where the numerator is equal to 0. To find the y-intercept, you make x 0. Well, that's easy. That just means you just take 0, plug it in for x into your equation, and you see what you get. Whatever you get, that's the y-intercept. Okay? And then finally, we're going to do this in steps. So there are some steps that have to be taken before others. So we're going to find the domain and the discontinuities first before we do anything else. Okay? Because the discontinuities involve us, right, actually trying to factor and cancel things out. And we want to use that canceled function to find things like the intercepts and other things like that. Okay, so now, here is what we are going to do for today. We are going to take some examples, And we are going to find the domain, classify each discontinuity as removable or non-removable, which is what we did earlier. And then, using the simplified function, we're going to find the x and y intercepts. Okay, we're going to find the horizontal or slant asymptote using our three cases. And then there's a couple more steps that come afterward, which will be in the next lesson. Check to see if the function will cross the horizontal or slant asymptote. We'll talk about that later on. And then we will then actually go ahead and graph. But for now, if you can do these three steps here at the top, you're pretty close to actually being able to make the graph. All right, so let's take a look at our first example. H of x is equal to 3 plus 2x over 1 plus x. The first thing we're going to do is find the domain. To find the domain, we're going to take the denominator, we're going to set it equal to 0, and we can say that x can't be negative 1. Now, we know that for certain. Now, I could come up here, I have 3 plus 2x over 1 plus x, and I could try to factor the numerator to try to cross out the denominator to figure out what type of discontinuity x equals negative 1 is. All right, but I can't cross anything out, so I'm stuck with what I have here. So my domain is negative infinity to negative 1 in the union with negative 1 to infinity, and I know x equals negative 1 is a non-removable discontinuity because I couldn't factor and cancel it out. So there will be a vertical asymptote at x equals negative 1 when I go to make my graph. Okay, that takes care of that. So now, my next step is going to be to find the horizontal or slant asymptote. There's going to be one or the other, never both. All right, so I'm going to look at the degrees. The degree in the numerator is 1. The degree in the denominator is also 1. So that means there's a horizontal asymptote, and I'm going to divide the leading coefficient. So it's going to be y equals, here's the leading coefficient here in front of the x, it's a positive 2. The leading coefficient here is positive 1, so I'm going to take 2 over 1, that's 2. So I know there's a horizontal asymptote at y equals 2. That's it for that. Okay, that helps me to make my graph. Next, I'm going to find my intercepts. Let's find the x-intercept. To find the x-intercept, we make y 0. So I'm going to set y to 0, 3x plus 2 over 1 plus x, or x plus 1. Now, to solve this, I need to set the top to 0. You could, if you want, if it helps you, multiply both sides by x plus 1, and then you'll see, oh, that times 0 is going to be 0. So I just need to solve where 0 equals 3 plus 2x. So x is going to be negative 3 over 2. So there's going to be an x-intercept at negative 3 over 2, comma, 0. There's my x-intercept. And then finally, I can find my y-intercept by setting x to 0. And I can do that by finding h of 0, which is going to be 3 plus 2 times 0 over 1 plus 0, which is 3 over 1, which is 3. So there's a y-intercept at the point 0, comma 3. Okay, so those are the first 4 steps that you're going to take here in finding your graph for your rational function. All right, let's try a second one. This one's a little more complicated. Let's try j of x equals x squared plus 9 over x squared minus 2x plus 3. The first step is we're going to go for the domain. To find the domain, we need to see x squared plus or minus 2x minus 3. It can't be 0. So I'm going to factor. I get x minus 3, x plus 1. I can split them. So I'd get x equals 3 and x equals negative 1. Those are my two restrictions here, my two discontinuities. So my domain is negative infinity to negative 1 in the union with negative 1 to 3 in the union with 3 to infinity. Now, I need to classify these discontinuities. I have x equals 3 as a discontinuity and x equals negative 1 as a discontinuity. But before I do that, I need to come back up here and try to factor the numerator. I already factored the denominator when I found the domain. I got to factor the numerator and try to cancel something out. Maybe I can, maybe I can't. So the top is the difference of two squares. Becomes x minus 3 times x plus 3. And now I can cancel out that x plus or x minus 3 term. So I'm left with x plus 3 over x plus 1. So my x equals 3 discontinuity is removable. I removed it, right? I took out the x minus 3. So there's a hole there. There's going to be a hole, well, at the point 3, comma, and I got to plug in x equals 3 to this equation that I just came up with. So that's going to be, we'll do it down here, 3 plus 3 over 3 plus 1, which is 6 over 4, which is 3 over 2. 3 over 2. Okay? There is my removable hole. So my hole is going to be at the point 3, comma, 3 over 2. X equals negative 1. Well, if I look at my function that I've crossed out, I couldn't cross out the x plus 1, so it's still there. So it's not removable. This is non-removable here. So there's going to be a vertical asymptote at the line x equals negative 1. All right, those are my two discontinuities, and they've now been classified. One's a vertical asymptote, the other's a hole. Okay, now let's go to my horizontal or slant asymptote. To find the horizontal or slant asymptote, let's take this function that's now been simplified. It has degree 1 on the top. It has degree 1 on the bottom. So the degrees are equal to each other. So I'm going to have a horizontal asymptote at the line where these two coefficients, there's a coefficient of 1 here, there's a coefficient of 1 here. So I'm going to take 1, divide by 1, and y equals 1 is my horizontal asymptote. No slant asymptote. There can be one or the other, never both. All right, let's go ahead and find my x-intercept. To find the x-intercept, you're going to make y 0. So I'm going to make y 0 on the function that I have crossed out. So I have x plus 3 over x plus 1. Again, you can multiply both sides by x plus 1 if you want, or you can just set the numerator equal to 0, because that's what's going to have to be done. And I get negative 3. So there is an x-intercept at negative 3, comma 0. And then finally, my y-intercept, I can find that by making x 0. Again, use the function that you have worked with and repaired already. So j of 0 is 0 plus 3 over 0 plus 1, which is 3 over 1, which is 3. So there's a y-intercept at 0, comma 3. Now, if I haven't been clear yet, you have to use this function that you've crossed out to find the x and y intercepts. You have to use that function. You cannot go back to the original one that's here. Okay? You have to use the one that you've crossed out on. All right, to find those two. Otherwise, you're going to get phantom points that don't exist on the graph. Okay? All right. So that takes care of that one. Last one. Let's try k of x equals 3x plus 1 over x squared minus 2x. So we are going to find the domain for this. So I'm going to take x squared minus 2x. It can't be 0. It has a GCF of x. I'm going to factor it out. So I can solve this. X can't be 0. And x can't be 2. So I know that for certain. So my domain will be from negative infinity to 0, in the union with 0 to 2, in the union with 2 to infinity. Okay. Now, my discontinuities are at 0 and 2. So let me come back up here. The denominator, I know it factors as x times x minus 2. The numerator cannot be factored. It stays as 3x plus 1. So I can't do anything with that at all. So since I cannot remove either the x or the x minus 2, then both of these are going to be non-removable discontinuities, and they're going to end up being vertical asymptotes on my graph. So there's going to be two vertical asymptotes on this graph, one at x equals 0 and the other one at x equals 2. Okay? So now we're going to go ahead and we're going to find the horizontal or the slant asymptote. Now from here, since I couldn't actually remove anything in terms of my discontinuities, when I find the horizontal slant asymptotes, the x and y intercepts, it doesn't matter which function I can use. I can use the original one or the one that I factored. It doesn't matter. It only really matters when you remove something. When you remove something, you have to use the one that you removed. Okay? All right, so if I look at the original one, it's just a little easier to get the degrees on this one. The numerator is degree 1. The denominator is degree 2. So the denominator has a bigger degree than the numerator. So the degree in the denominator is larger than the degree in the numerator. So that means there's going to be a horizontal asymptote at y equals 0. This is the case where you don't have to do any work. You just have to know that if the degree underneath is bigger than it is up top, then y equals 0 is the horizontal asymptote, and it's done. Okay? All right, let's find my x-intercept by making y 0. Okay, so I'm going to set y to 0. And again, it doesn't matter which function you can use. You could use the original one or the one that you factored. It doesn't matter. The x times x minus 2 will cross out if I multiply by it. So I end up with 0 equals 3x plus 1. So x comes out to be negative 1/3. There's going to be an x-intercept at negative 1/3, comma 0. And then my y-intercept, again, the same thing. It doesn't matter whether or not you use the one that's printed. To find that, I'm going to make x 0. So I have k of 0 will be 3 times 0 plus 1 over 0 times 0 minus 2, which actually comes out to be 1 over 0, which is undefined. So there's no y-intercept. There's no y-intercept at all. And that should make sense to you because there's a vertical asymptote at x equals 0. So when I graph this thing, the y-axis is actually a vertical asymptote. So the graph can't touch the vertical asymptote, right? So how could there be a y-intercept, right, if it can't touch this line? Okay, so that's the algebra telling you that, hey, look, you saw that over here. Here's a reminder, right, that there can't be a y-intercept because you can't touch the y-axis this time because there's an asymptote there. All right? Okay, so that is your 3 examples of this. So what I want you to do, obviously, is to practice all of these steps that we've taken, and then we'll continue on in the next lesson with more steps and actually going ahead and making the graph. Okay? As always, thanks for clicking.